Welcome back to Inorganic Chemistry. In this lecture, we'll look at the main group chemistry of the group 3A elements. The group 3A elements do not have a special name, unlike the groups we looked at already, the alkali metals, the alkaline earths. And one reason, perhaps, is historically it's been hard to recognize how these groups of elements work together. So we're going to use our guiding principles so far to help us understand how the group 3A elements work. So periodic law, the periodic trends would say that things like the electronegativity decreases going down the group. The uniqueness principle says that boron is different than the other elements in the group, and that is true. Boron, for example, is the first non-metal we're going to be talking about, whereas aluminum is a metal. The diagonal relationship, we saw in the previous lecture that beryllium is similar to aluminum, and boron is going to be similar to silicon. The inert-pair effect, we're going to learn about that in this group when we get to thallium. You would expect the charge on these elements to be +3 because they're group 3. When we get to thallium, we'll see that +1 is the most important oxidation state. The metal-non-metal line on the periodic table goes right through this group, and we'll see that. And of course, that's going to affect the chemistry. It's this acidity, basicity character. The boron oxides, or boron hydroxides are Lewis acids, whereas aluminum oxide is amphoteric, and the other oxides are basic. Standard reduction trends. As we go down the group, the standard reduction potential increases, but of course there are some jumps and exceptions. Okay, since this group has some unique properties, I'm going to go element by element, and first we'll start with boron, of course. And it was known for a long time as a component in borax. B2O3 is the formula of borax, so it's a weak acid, and once the boron was isolated from that, the structure has different allotropes, which are when you have different phases or different structures for the same element. But one of the structures is B12, which forms icosahedra, which are stacked in the solid state. So this is the graphic on our splash screen, is elemental boron. Now boron has 3 valence electrons, so borane, like methane, the similar naming, the borane is electron deficient. The boron doesn't have as many electrons as carbon, so when it makes hydrides, it doesn't have enough electrons to fulfill its octet. So that's what electron deficient means, less than octet. And this is diborane, actually. It has a 3 center, 2 electron bond, like we mentioned when we were looking at beryllium, and we'll learn a lot more about the boranes next week when we spend a lecture on that. So boron, we said, is our first non-metal. This area of the periodic table are the non-metals. The rest of the periodic table are the metals. The line between them is defined right here, between the boron and aluminum. And step on over here. Okay, so we would expect aluminum then to be a metal, boron to be a nonmetal, although actually the elements right here along this border are considered metalloids because they're at the borderline. They're not quite metals, not quite nonmetals, or sometimes act like metals, sometimes act like nonmetals, so they're called the metalloids. Aluminum then should be a metal, and indeed it has shiny, it's solid, it's malleable, it has all the properties of a metal. It's also it's the third most abundant element in the Earth's crust, but before 1886 it was considered a precious metal, and here is a drawing of the setting of the 100-ounce square pyramid atop the Washington Monument in D.C. of this solid block of aluminum as a way to honor our first president. In 1886, Charles Hall, undergraduate chemistry major at Oberlin College, and Paul-Louis Héroult in France simultaneously, separately, discovered how to isolate aluminum electrochemically from bauxite, a common aluminum ore, dissolved in molten cryolite. So this takes a lot of electricity, but it makes aluminum a lot cheaper than precious metals, for example. It's one of the cheapest metals because it's so abundant in the earth. As long as we add energy, we can get it. So we can make aluminum cans and aluminum foil and disposable material out of aluminum now. Gallium should also be a metal. It has the interesting property, though, that it's not quite a solid at room temperature. So the melting point, 29.786, means that it won't melt in your hand, but it will melt in your mouth. And this has led to a trick called the disappearing spoon, where you have a shiny metal spoon, looks like any normal, silverware, but when you stir it in your hot coffee or hot tea, it melts and disappears. So this book here by Sam Keene has lots of stories of the elements like that. Gallium today is, you can look up on YouTube, you can watch a disappearing spoon video. I don't recommend you actually drink it. Today gallium is useful in semiconductors, such as the devices like light-emitting diodes, where depending on what it's compounded with changes the band gap and therefore changes the color. As we keep going down the group, we get to indium, which is named after the color of its atomic emission. In the spectrometer, it gives an indigo color. Thallium was similarly discovered by its emission. It gives a green color, and thallus means green, so hence the name thallium. The thallium compound, though, like thallium sulfate, used to be used as rat poison, since thallium is highly toxic. But if we look at here, sulfate is a 2- polyatomic ion. There's 2 thallium ions, so that means thallium is in the +1 oxidation state. But wait, it's in group 3A. How come it's +1? This is an example of what's called the inert-pair effect, where these s electrons here in the valence shell are not very reactive. They're inert, probably because these f orbitals and d orbitals don't shield them very well from the nucleus. So here, as we go down the group here, here's the electron configuration, and here's the sum of the second and third ionization energies. So as we expect, it decreases as we go down, but there's this jump here. When we go from aluminum to gallium, it goes up because these d electrons aren't shielding these s orbitals as well, and so they're feeling the nucleus more than these s electrons. Then we go down again, but then when we get to thallium, it jumps up again, because now these f orbitals, as well as the d orbitals, are not shielding very well. So we'll see this becomes important as we keep going to further groups in the periodic table.